We're now going to look at the time-dependent Schrodinger equation, and we'll see how we can get there from our previous relation, which was the time-independent Schrodinger equation. And the reason we'll need time dependence is when we look at situations where the total energy E does change with time. So for example, if a particle scatters in the system, you can have a total change of energy of the particle, or for example, when you are changing from the energy levels in an atom, which we'll look at later. So what we can do is go back to our separation of variables, and if we take the time derivative of that, we can get a relation. So let's show that. So you have the time derivative of the plane wave, and we show this again from our separation of variables, that we have this was the time component, and this was the wave function that we had that was only dependent on position, psi x. And if we take the time derivative of that, we get the negative I comes out, as does the omega, and then that's multiplied by e to the I omega t times psi of x, and we see that this is just our original waveform when it's a function of x and t. So we have this negative I omega in front, and what we can do now is write that in terms of the total energy. So we can use the relationship that we had before, where with Planck's law, E equals h nu, and nu is omega over 2 pi. And we know that h over 2 pi is h bar, so that's another way of writing the Planck relation, E equals h bar omega. And then what we can do is just rewrite this as E times the wave function. And why do we do that? Because we saw from above that we have in the time-independent Schrodinger equation, there's this term E times psi. So if we now write this as E psi of x of t, we get that that is equal to negative h bar over I times this derivative of psi, the time derivative. Okay, so we just got that from the equation above, substituting in that omega is E over h bar. Okay, now we can get rid of the minus I and just call it I, because what we remember is the relation that I is the square root of minus 1. So we have minus 1 over the square root of minus 1, and that just becomes the square root of minus 1, which is I. So there's an identity that minus 1 over I is equal to I. So that's simply I h bar d psi dt. Okay, good. Now what we can do is replace that in the time-independent Schrodinger equation. And what we need to do, of course, is that where we had psi of x, this is now going to be, we're putting back in the time dependence. But if we go back and use this relation that we had, we can write this out as negative h bar squared over 2m is multiplied by the second derivative of x squared, and that's equal to, now we have this term, we're replacing e psi with I h bar d psi over dt, and then we still have the minus the potential energy times psi. Okay, now we're basically done, except that we can rearrange this a little bit, since typically we have this time derivative shown on the left-hand side of the formula. So that would mean moving over the second derivative of position just to the right-hand side. Notice that the signs are okay because I basically moved the v. If you move the v over there and then you flip the equation around, the signs make sense. Okay, so that's it. So this is the time-dependent Schrödinger equation, TDSE. And one thing that we'll look at on the next slide is this graph here, which is showing that wave packets in certain situations do change with respect to time. And in fact, an interesting situation is where there is no potential energy, where we call it a constant value equal to 0. So this is when V is equal to 0. And in that case, the total energy is the kinetic energy, capital K, plus V, but again, V has gone to 0. So that's equal to K, which is, for this non-relativistic particle, the momentum squared over 2 times the mass. Okay? And what we'll see in the coursework is that if you use the plane wave, you can substitute in a relationship which is a dispersion relation, where you have to think about what omega is. Now, I'll leave that for the coursework, but what we can show, which is a bit different, is just the consistency of the result that we're going to show. So what we're going to show is that the omega, the angular frequency, depends on the wave number. So it's a function of k. And that functional form is h bar times k squared divided by 2m. Now, what you'll see in the coursework is that when you look at the wave function, psi, you now, for this wave that's propagating freely, meaning that it doesn't experience potential energy, when you plug it in here, you now need this omega term, which is dependent on k. All right, but again, I'll leave it for the coursework for you to plug that in to the time-dependent Schrödinger equation and show that this relationship for omega holds. But what we'll do here is we will look at the consistency, assuming that we're given this, and in terms of what we've done before, which is basically the de Broglie wavelength and the Planck relation. So as we had before, the total energy is equal to h bar omega, and in that case, that's also going to be equal to we just saw above that since V is 0, this is now equal to P squared over 2m, and again this is for a free wave packet. All right, and that's fine. Now we can write that as omega is equal to P squared over 2m h bar. Let's go back up here and think about what k is. So k is 2 pi over lambda, and this is where we use the de Broglie relation that lambda is h over p. So this now becomes 2 pi p over h, or in other words, p over h bar. Okay? Now, let's then plug in the rest of this relation. We want to square this thing, so let's look at this whole thing squared. So that now becomes p squared over h bar squared, and in this given relation we also multiply that by h bar over 2m, and we see that this now gives us the same relationship that we saw over here when we wrote this in terms of the kinetic energy, which was just this p squared over 2m multiplied by h bar. So we have consistency. Now, why is this important? It's important because whenever we have the omega depending on k, this is saying that the wave packet's group velocity is going to be different than phase velocities. And we can argue, as is done in the lecture notes, that this gives you a situation where over time the wave packet spreads out, it disperses. And we see that in the lecture notes by going back and looking at our definition of our Gaussian wave packet, and we had there a quite relatively complicated mathematical form of the Gaussian where we were integrating over this very large number of waveforms that again followed a Gaussian shape with a spread in k. And then when we did that is when we saw the uncertainty principle, such that the tighter or the smaller the distribution in the wave number, then the larger the spread in the waveform in terms of its position x. Or other way to put it is that if you had a wider distribution in the k, you got a tighter distribution in x. And I don't expect this to be shown mathematically on an exam or any coursework, but I include it in the lecture notes as it shows where you get this result shown in the graph. And it explains how you get, as time progresses, this spreading waveform. So Maybe don't worry too much about that, but if you want to look at the details, you can.